Okay, ladies and gentlemen, welcome back to Mr. Lee Physics class. So today we'll learn, yesterday we learned the self-induction. So today we'll learn another induction we call mutual induction. Let's look at the diagram. The diagram shows that there's how a power plant generate the electricity and then through the power line sent to the consumer. So in between, we have the step-up transformer and also step-down transformer. Ladies and gentlemen, what we will learn today in this lesson, we learn about the mutual induction. Let's look at the objective for today's lesson. In this lesson, you will learn to explain the phenomenon of mutual induction and define the mutual induction, inductance. And objective 2, to derive an expression for mutual inductions between two coaxial coils. That means two solenoid. All two coins, choose object with the shape of coins. The derive objective 3, to derive and use the equation of Vs over Vp equal to Ns over Np for a transformer. And last, about eddy current in the transformer. Ladies and gentlemen, let's observe the slide. Now we have two coins or two solenoid. Let's say we have coin P and we have also the coin X. Coin P and coin X are in different number of turns or that have the different characteristic. Ladies and gentlemen, we look at here, the coin P, a solenoid or a coin P is connected through an ammeter and is given by a direct current power supply. Where the second coin S, is just connect to a resistor and go through a galvanometer. Now, what happens when the switch is connected? Once the switch is connected, the current increases. Once the current increases, the magnetic field also increases. And at that moment, initially, that is neutral, right? Coin S is neutral. Once the magnetic field produced, there is a change of the magnetic field, so current induced. So again, once I connect it, so the pointer is deflected. Once I open the switch and connect, then what happened? The pointer will move to the other side as well. So that means that the deflection when connect the switch is moved to deflect to left side. But once I unplug it, it's deflect to right side, left, right. So now with the slow motion, we observe the change. Current increase slowly. When there is the increasing of the magnetic flux, the current in the coin S also increase gradually. Again, increase until the magnetic field become maximum and remain in the situation of maximum. The current will back to zero. Why? Because there is none of any change of the magnetic field. Okay, for the formula of mutual induction. As we know that the EMF is directly proportional to negative change, the rate of change of the magnetic flux, where the flux is equal to B times with A. And also B is directly proportional to the current. As a result, because B is directly proportional to current, that means we can say that the magnetic field is directly proportional. The magnetic field produced in the first or primary coil that is directly proportional to the current supplied to the coil. As a result, we said that the EMF is directly proportional to negative dI over dt. Why negative? Because that is explained by the whose law? That is Lenz's law. Because the induced current or induced EMF, induced current is flow in opposite direction of the magnetic effect to produce it. And finally, EMF is equal to M negative M dI over dt. Because it's directly, EMF is directly proportional to dI over dt. That means that because this is, we are using the solenoid, so we need to use the M. M is known as the mutual inductance of the circuit, where the unit of the mutual induction is Henry. Still in the unit of Henry. That means 1 Henry is equal to 1 watt second, 1 watt second per ampere. Ladies and gentlemen, yesterday we learned the formula for self-induction. Self-induction, EMF is equal to negative L times with dI over dt. But for the mutual induction means that the first coil is magnetized by a source. This means if the first coil consider, just now the first coil consider is the mutual induction, is the self-induction with the first induction. This induce, what is that? The magnetic flux produced will magnetize the other coil or the coil near or inside the magnetic field that produced from the coil P. So current induced in the coil S and two of the solenoid which are connected separately with the same magnetic field. We call that the total. Here got the inductance, right? Coil P with its inductance, coil Q with another inductance. So the resultant induction will be the mutual induction, the combination of the inductance of P and inductance of S. Now we look at the situation. Now, what happened? Same thing, right? So what happened to the step 1, the induced EMF in coil S, where EMF in the coil S is equal to negative M di over dt. Using the Faraday's law and Lenz's law, EMF is equal to negative N number of turns of the S. Okay, because this induced, right? So times with ds, the change of the rate of change of the magnetic flux in the coil X. So where the rate of change of the magnetic flux is the rate of the change in the coil S. By equating the EMF for coil S, we get that negative M equal to dip over dt equal to negative ns d phi s over dt, change of the rate of change of the magnetic flux. So dt, we cancel each other. So at the end, we found that by integrating the equation, we found that M is equal to ns phi s. That means that change of the magnetic flux over the current in P. Why? Because the current, okay, EMF is the induced EMF. This current, the mutual inductance, it depends on the current, okay, on the current that produces it. If the current is smaller, the smaller the current, the greater the mutual induction. Definition. Definition of the mutual induction M is equal to ns phi s over ip, where the mutual induction is directly proportional to the number of turns of the solenoid S. It's directly, easiest we said that it's directly to the coil S, but inversely proportional to coil P. Okay, so inversely, what is the inversely? Just the current in the coil P, inversely proportional. As a summary, not yet, let me see. 2, 3, 4. Okay, another slide. Okay, in general, the mutual induction between any two coils depends on the number of turns of the coil, the cross-sectional area of the coil, the shape of the coil, the distance of separation of the coil, the relative orientation of the coil, relative, that means relative motion, yeah, and the type of medium of the coil. So here, number of turns, that means how many turns. Cross-sectional area depends on the size of the solenoid, both solenoid. Shape of the coil, that means either the shape is okay, big or smaller the coil. Okay, so and the distance of separation of the coil. So between the two coils, relative motion, that means that is it any motion between the okay move towards or move forwards, move faster or slower, okay, to each other. Type of the medium, either there is a soft iron core, present of the soft iron core or not. Ladies and gentlemen, as a summary, the phenomenon in which an EMF is induced in one coil due to a changing current in a neighboring coil is known as mutual induction. The EMF induced in coil S is equal to negative M d change of the current in P over T, di over dt. And the mutual induction is equal to Ns phi S over Ip. Okay, this one is EMF, how many volt? This one is the inductance, the ability of the second solenoid to induce the current. And the unit for the inductance is Henry. For the next slide, observe that there are two solenoids with the cross-sectional area of P. When the coin S is moved, is worn around or moved on the coin P. Consider NP is the number of turns of the coin P. LP is the length of the coin P. AP will be the cross-sectional area of the coin P. And IP is the current in coin P. BP will be the magnetic field in the center of coin P. And NS will be number of turns of the coin S. AS will be the cross-sectional area of the coin S. Okay, now for the assumption, we look at the assumption first. Assumption AS is equal or almost equal to AP. Okay, AS is greater a bit but almost equal to AP. Okay, that means it can one on it, but just okay, just the size is just can fix or just can go through the coin P enough. Don't be too loose. Okay, so that reason, so that all magnetic field line from coin P pass through the coin S, cut by the coin S. Coin P, the coin P is assumed to be an infinity long coin. Okay, P consider is very long, so that the magnetic flux density at the center of the coin is uniform. So this means that the magnetic field produced is uniform. Derivation. The magnetic flux density Vp at the center of the coin P, Vp is equal to mu, okay, Np Ip. Np will be the number of the turns per unit length. Np, that means Np equal to capital N number of turns over Lp. Okay, number of turns per length is equal to the how many number of turns of P per length. The magnetic flux through each turns of coin, that means it will be equal to Bp as. Okay, and it will be Bp AP. So from here, the total magnetic flux to Ns turns N turns of a coin S. That means Ns times with the magnetic flux of S equal to Ns Bp AP. Okay. At the end, Ns phi S equal to Ns mu naught Np Lp Ip AP. Then, by definition, the formula, the mutual induction M is equal to Ns phi S over Ip. That means that the number of turns of the solenoid S for the coin S times with the magnetic field, magnetic flux. The magnetic flux actually is from the P, right? So it will be equal to mutual induction times with IP. As a result, the mutual induction is equal to mu naught AP, NP, NS over LP. So that means mutual induction is directly proportional to the number of turns of P. It's also directly proportional to the number of turns of S. It's directly proportional to the cross-sectional area of P. The bigger the P, the stronger the magnetic flux. Okay, times with that is directly proportional to the mu naught and inversely proportional to length. Okay, the longer, actually, it will become smaller, the mutual induction. Okay. Ladies and gentlemen, let's look at the coin of two coins of wire are worn on an iron core. The current supplied to the primary coin increased uniformly from 0 to 0.6 ampere in 5 seconds. Then decrease uniformly to 0 in the next 2 seconds. When the current increasing, the EMF of 60 milliwatt is induced in the secondary coin. Question: calculate the mutual inductance of the coin and the induced EMF in the second coin when the current is decreasing. So how to solve it first? Step 1, when the current is increasing, dIP over dt is equal to is equal to 0.6 over 5. We get that the change of the current in coin P is equal to 0.12 ampere per second. Every 1 second is produced 0.12 ampere. And mutual induction is equal to EMF of S divided by dIP over dt. So we get that it will be 0.5 Henry. When the current is decreasing, that means that dIP over dt, that will be 0.6 over change of time in 2 seconds. So it will be negative 0.3 ampere second. So the induced EMF in the coin S, second coin, will be equal to negative M dIP over dt. So mutual induction, we get that is 0.5 times with 0.3. So that means that it will be 0.15 watt only. Okay, so that means that this is how we get the, how we calculate the answer. So the induced EMF, they didn't ask about the direction. They just want the magnitude at the end. EMF never show the direction, just the current show the direction. So current will be in negative direction, but EMF, just a magnitude without any direction, so it will be positive. As a conclusion, we said that the mutual induction between the two coaxial coils M is equal to mu naught AP NP NS over LP. That's all for today's lesson. So here, the mutual induction, remember class, the mutual induction, just apply the formula to solve it. So as usual, later I will post the question in our Telegram group. So I want you all solve the question before checking the answer. Ladies and gentlemen, here will be the question. So today's lesson, we have 5 questions. Question number 1, question number 2, question number 3, and question number 4. Last question number 5. So we just solve the 5 questions only. Okay, actually in this worksheet got some other question. So other question already out of our syllabus. Okay, so thank you and see you again tomorrow. Okay.